So in this video I'm going to go over the GCSE Chemistry, Unit 1, 2024 paper. Okay, on to just question 1. Here's a question about the periodic table. We've got an outline of the periodic table. And part A, select the correct symbol. Now you need to be careful with these types of questions. Sometimes it says name, other times symbol. So be careful that you do the right thing. If it says identify, then you can give either the name or the symbol. So part 1, which element has 5 electrons in the outer shell? Well, group number equals the number of electrons in the outer shell. So here we've got group 1, group 2, 3, 4, 5. Arsenic. So we're going to write down AS. Part 2, which element has 3 shells containing electrons? Well, the periods equals the number of shells. The horizontal rows are known as the periods, so that's period 1. People often forget about that. So hydrogen, and this would be helium. So that's period 1, period 2, period 3. So these period numbers equal the number of electron shells. Well, magnesium has 3 electron shells. It actually has an atomic number of 12. It has 12 electrons, 282. So again, I'm going to write down Mg. Which element forms an ion with a 2- charge? So in this instance, the atom is going to have gained 2 electrons. Now, it's not going to be magnesium. It has 2 electrons in its outer shell, which it would lose. So that is 282. So it's going to lose those 2. That will become 2+. Whereas over in group 6, if we take oxygen as the example, 2, 6, to obtain a full outer shell, that would be gaining 2 electrons to become 2, 8. And you're adding 2 negatives onto a neutral atom. So then that would become 2-. So the element which forms an ion with a 2- charge is oxygen. So O. Which element is a transition metal? Well, this part of the periodic table is where you find the transition elements, Fe. Part 5, which element forms an ion with the same electronic configuration as argon? Well, you can use your periodic table to find argon. It's a noble gas. It's going to be over here. Now, argon has 18 electrons. So what you have to do is find an element which has 18 electrons when it becomes an ion. Now, if you go to the metal of the next row, so we're going to look all the way down here, potassium is 2881. 2881. It's going to lose that electron when it forms an ion, and now you can see that it's 288. And argon is also 288. So potassium is the answer. Part B, how are the group 1 elements stored in the lab? Well, they're in oil. And that's like paraffin oil. That's to stop them from reacting with the oxygen in the air. It also prevents moisture from reacting as well. Part 2, state the name by which the group 1 elements are known. And that's the alkaline metals. Just be careful that you don't lose a mark here by saying the alkaline metals. Part 3, explain why group 1 elements show similar chemical properties. Well, chemical properties have to do with the number of electrons in the outer shell. And all of the group 1 elements have 1 electron in the outer shell, and that's why they react in a similar way. So there are a couple of alternatives as well. Part 4, state and explain the trend in reactivity down group 1. Well, metals get more active as you go down the group. That applies to all metal groups. So the trend is that the reactivity increases. I'm just going to draw a sketch over to the side to help explain that. So here is lithium, and then I'll just do sodium. So there are 2 electrons there, then 8, and then that's the outer electron. You can see that the outer electron in the sodium is further from the nucleus, and this outer electron is attracted to the nucleus. So it's further from the nucleus than it is in lithium. And because this outer electron in sodium is further from the nucleus, it's less attracted to it, and that means that it's easier to lose this electron than it is to lose this electron. You could also talk about shielding. So maybe instead of this line here, you can see that the outer electron in the sodium has got an extra shell of electrons, and this shell of electrons shields the outer electron from the nucleus. So you can see in lithium it doesn't have that shell of 8 electrons. So you could, instead of this here, also say that the outer electron is more shielded by the inner electrons. See part 1. 2 observations which are made when a piece of potassium reacts with cold water, which are not made when lithium reacts. Well, potassium burns with a lilac flame. Obviously, lithium's not going to do that. And the reaction of potassium is more vigorous than the reaction of lithium with water. And the potassium crackles at the end. If you can remember seeing this being demonstrated to you in the lab, the potassium floats and moves across the surface with a lilac flame, and then at the end you get this crack. There is a lot of heat produced in this reaction of both potassium and lithium, but the reaction with potassium and water produces a lot more heat. And so the potassium actually melts into a ball, which does not happen with lithium. Part 2, a half equation for the formation of a potassium ion from a potassium atom. For this type, remember, half equation means there are electrons present. And start off by looking at how it's worded. The formation, to that's arrow. Formation of a potassium ion. So this is going to be on the right hand side. A potassium ion is K plus. And now it's from a potassium atom, so this is going to be on the left hand side. Now to go from here to here, an electron is lost. So on the right hand side, I can put plus E minus. You would also get this marked right if you move the electron to the other side. So for example, potassium atom minus E minus goes to give K plus. So that's another way of writing it, although it's conventional to write it like this. 2a, part 1, a dot and cross diagram to show how magnesium chloride forms. Well, magnesium is a metal and chlorine is a non-metal. If you look of where they're at in the periodic table, the magnesium's to the left of the zigzag line and chlorine's to the right. And if you have that scenario where the metal and the non-metal react, it's going to be an ionic bond. And that's the transfer of electrons. So start off by drawing the magnesium and chlorine atoms. 2 chlorine atoms are required because the magnesium has to lose 2 electrons. So one of the electrons will transfer to this atom. This electron then will have to transfer to another chlorine atom. So here I'm just going to draw in the symbols, so Mg, magnesium, and then the chlorines. And then you've got to show these atoms becoming ions. So we've got the magnesium ion, which is formed whenever the outer 2 electrons get lost. So 2 electrons in the first shell, and then 8. And you've got to show the charges on the ions. So brackets around it, and then 2 plus outside, or you could do Mg2 plus. You then do the same thing for the chlorine or the chloride ions. And you can see here that I've drawn the additional electron as an X to show that it has come from the magnesium. Again, square brackets, and then minus outside, or you could just say Cl minus. On to part 2. 2 physical properties of magnesium chloride. Well, that is just the same as asking you to give 2 physical properties of an ionic substance. So their properties are typically things like high melting point or high boiling point. Don't say MP and BP, write out the full word, or you can say they're solids. Ionic compounds generally are soluble in water. And you could also say that they conduct electricity when molten or aqueous. Remember, they don't conduct electricity when they're solid. B part 1 then is asking us to draw a dot and cross diagram to show a molecule of hydrogen chloride. So these are non-metal elements, hydrogen and chlorine. And when we draw dot and cross diagrams, it's usual to draw the outer shell electrons only. Now, it doesn't ask us here to show the outer shell only, but that's what we tend to do. So I'm going to draw a hydrogen, and then this would be the chlorine. One electron from the hydrogen, and then the chlorine has 7 electrons in its outer shell. Now, you don't have to draw the shells. You could just draw it like this. That's fine. And then it says label a lone pair of electrons. Well, here is a lone pair, here, here. That's all I need to do. It just says a lone pair. On to 2. Balance sum of the equation for the formation of this from hydrogen and chlorine. Now, hydrogen and chlorine are diatomic gases. So it's H2 plus Cl2 goes to give HCl. And then to balance it, a 2 is needed in front of the HCl. Part C. State the bonding in magnesium chloride. Well, metal, non-metal, so that's going to be ionic, or it's going to form positive and negative ions. So that's ionic. And the structure of that is giant ionic or ionic lattice. Hydrogen chloride, the bonding in it, now it's not between the molecules. When it's just asking you for the bonding in a molecule, that means between the atoms. That's going to be covalent. And the structure of that is simple covalent or molecular covalent. Question 3, complete the table. The pH of sodium hydroxide here is 12, obviously. Phenolphthalein in an alkaline solution is pink. So we put pink in there. Remember, phenolphthalein is colourless in acid. Hydrochloric acid is a strong acid. It's going to have a pH of around 1. And the universal indicator is going to be red. Now, for the hydrochloric acid, you could say 0 as well, 0, 1, or 2. Generally, 0 to 2 are considered strong acids at GCSE. Part B, write an ionic equation to show the complete ionization of sulfuric acid. Now, sulfuric acid is H2SO4. And when it ionizes completely, if you imagine, this part breaks. And it breaks up into hydrogen ions and sulfate ions. So we've got H plus ions, and there will be 2 of them, because there's a 2 here, plus sulfate ions. Part 2. State how the pH of a sulfuric acid solution changes as the concentration of hydrogen ion increases. Okay, I'm just going to draw out part of the pH scale. Now remember, acids produce hydrogen ions in solution. And the more hydrogen ions there are, the lower the pH will be. So if you imagine down here, there'll be lots of hydrogen ions. And then as we move up the scale, as the pH numbers get larger, there won't be as many hydrogen ions in solution. So going back to the question then, what happens to the pH as the concentration of the hydrogen ions increases? Well, you can see here that as the hydrogen ion concentration increases, the pH number decreases. A common mistake there is people think, Okay, as the hydrogen ion concentration increases, it becomes a stronger acid, which is correct. And then they put down that the pH increases as well. But remember, when the pH increases, it's actually becoming more alkaline. So the higher the concentration of hydrogen ions, and the smaller or the lower the pH value is. See part 1, what is meant by the term salt. So it's just a standard definition. Part 2, write the formula of salt A. Okay, so let's see what's happening here. I've got hydrochloric acid and a metal. So metal plus acid gives us salt plus hydrogen. So remember MASH for that. When hydrochloric acid reacts, it forms chlorides. And the first part of a salt is usually a metal, which in this case is zinc. So the salt will be zinc chloride. It's asked for the formula, so don't give the name. Identify gas B. Okay, well, we've already talked about how metal plus acid gives us salt plus hydrogen. So that is going to be hydrogen. And then the test for it is a lit splint pops. Part's pretty, write the formula of black solid C. I've put the reaction down here at the bottom. So let's see what's happening here. We've got hydrochloric acid and it's forming copper chloride. So this must be a copper compound because copper does not react with an acid. Copper's unreactive. So this is going to be an oxide of copper because it's black. So it's going to be copper dioxide, which has the formula CuO. Part 5, explain why an excess of the black solid, which is copper dioxide, is used in reaction 2. Well, that's just to make sure that all the acid gets used up. And then a balanced equation for reaction 3. So we've got sodium carbonate, which is Na2CO3, plus hydrochloric acid, HCl, and then it goes to give sodium chloride plus water plus carbon dioxide. And to balance it, then we need a 2 there and a 2 in front of the HCl. Okay, so I'm just going to plot this graph. So it should look like that. Again, it's a curve and you draw it freehand. Don't use a ruler to join the dots. The questions then are going to be based on the graph. What's the solubility at 90 degrees C? So I'll insert the graph that I had drawn. And now I'll go to 90 degrees C, go up, and it's around, I think that's 160. So it's going to be 160. Again, just be careful of how you read your own graph. Part 2. 28 grams of the solid are mixed with 25 grams of water. Explain whether it's saturated or unsaturated. So for this type of question, you need to remember that the solubility curves are always drawn in grams per 100 grams of water. So you've got to convert this in the question to look like this in the graph, if that makes sense. So what I mean is, I'm going to multiply this by 4. So that will turn to 100 grams of water. Therefore, I multiply that by 4. And so this becomes 112 grams. So what I can do now is go to the graph, 60 degrees C, and see what mass dissolves. So 120 grams dissolve at 60 degrees C. So that is the mass required to saturate the water. 100 grams of the water. So over here, I've got 112 grams per 100 grams, but at 60 degrees C, the water can hold 120 grams. So this here is going to be unsaturated. So again, questions like this, just convert this to 100 grams of water first, and then whatever you do here, you've got to do here. Then look at the graph. Part 3, calculate the mass of solid that will crystallise, in other words, appears a solid, when a saturated solution containing 40 grams of water, okay, so it's not 100 grams, and it's cooled from 70 to 20 degrees C. Remember, this graph from 70 to 20 is showing what happens when 100 grams of the saturated solution is cooled. So I'm going to work it out from this graph first. The solubility at 70 degrees C is about 132. That's grams per 100 grams of water. The solubility at 20 degrees C, well, from my graph, it looks like, if I can see that, yes, zoom in a bit. So 2, 4, 6, it's about 86 or 87. So if the question had said that a saturated solution containing 100 grams of water is cooled, then the difference would have been 45 grams. But remember, that is for 100 grams of water. So what you've got to do now is convert that to 40 grams of water. So let's see, so 45 grams in 100 grams of water. So we want to go to 40 grams. So basically, you divide by 100 and then multiply it by 40. And you get 18 grams. Part C is about testing for magnesium and chloride ions. So we have to give chemical tests that could confirm the presence of these. So I'm going to start off with the magnesium ions first. Now what we can do for this is add sodium hydroxide solution. And again, do make sure that you put in the word solution here. Don't just say sodium hydroxide. You don't need to say dissolve the magnesium ions in water because they're obviously already dissolved in the water because it's seawater. And when you add sodium hydroxide solution to a solution containing magnesium ions, a white precipitate forms, or a white solid forms. And this precipitate remains, so in other words, it does not dissolve when excess sodium hydroxide is added. Now hopefully you remember that aluminium ions and zinc ions also produce a white precipitate when sodium hydroxide solution is added. However, when excess sodium hydroxide is added, the precipitates of the aluminium and zinc will actually dissolve again. So that's how the magnesium ions can be distinguished from aluminium and zinc ions. Okay, so now I will do the chloride ions. And the test for halide ions is to use silver nitrate solution. Again, don't just say silver nitrate. And for chloride ions, you get a white precipitate or a white solid. So let's just check. I've done reagents, the positive test. So now I need to write ionic equations for the reactions. Obviously, I'll do the magnesium one first. So we've got magnesium ions. They react with the hydroxide ions in sodium hydroxide to form magnesium hydroxide. That's the white precipitate. Now you can see we've got two OHs on the right. Need to put a 2 there. And for the chloride ions, well, the halides, in this case the chloride ion, reacts with the silver ions, not the nitrate ions. There's going to be Ag plus Cl minus gives AgCl silver chloride. The silver chloride is the white precipitate. So on to 5. A part 1. Now I'm sure you've seen small packets of these put into shoes and electrical equipment. So if we just read through the information to start with. So a small packet may be added to the silica gel. A colour change from blue to pink is observed as the silica gel absorbs water. So even if you didn't know what a desiccant was, this is the clue here. Right? It removes water or moisture from the air. So it acts as a drying agent. That obviously then helps to keep the product dry. Part 2, name another compound which could be used in place of anhydrous copper 2 chloride. So just think what's happening. We've got anhydrous copper 2 chloride. And when it absorbs water, it changes colour, blue to pink. So you've got to think, okay, is there another anhydrous compound that could change colour when water's added to it? And the one you would have looked at probably is anhydrous copper 2 sulfate. So remember, it's white, and then it changes to hydrated copper 2 sulfate, which is blue. Part B. So we've got this solution. It contains 0.15 moles of copper 2 chloride. So I'm just going to write it underneath here, not 0.15. And it's mixed with another solution containing 0.26 potassium hydroxide. So again, I will put that in there. So part 1. How many moles of potassium hydroxide are required to react with the 0.15 moles? Well, you can see here that it's a 1 to 2 ratio. So if you start off with 0.15 moles of the copper 2 chloride or the cobalt 2 chloride, then that will react with twice the number of moles of potassium hydroxide. So in this case, that would be 0.3. Part 2, which reactant is limiting? Well, we've just established that we have 0.15 moles of the cobalt 2 chloride, and it will react with 0.3 moles of potassium hydroxide. Now from the question, there are only 0.26 moles. So we don't have enough moles to react. Remember, to react with this, we need 0.3 moles of potassium hydroxide. But we only have 0.26 moles, so we don't have enough. Therefore, the potassium hydroxide is limiting. Part 3, how many moles of the cobalt 2 hydroxide are formed? So in this type of question, you always use the limiting reactant to determine the product. So I'm going to use this value here, not this one. This is excess. So this is limiting. So we're going to work out the moles of copper hydroxide, which is this one here. Now you can see this is a 2 to 1 ratio. So if there are 0.26 moles of this, then it's going to form, in theory, half the number of moles here, which is 0.13. And then part 4, calculate the mass of the cobalt 2 hydroxide formed. Well, we've got the moles, 0.13. You've got to work out then the RFM or the MR of the cobalt 2 hydroxide. It is 93. And that gives an answer of 12.1 grams. Part C. Let's see, we've got 3.57 grams of the hydrated salt. And when it's heated to constant mass, 1.95 grams of the solid remained. Calculate the number of moles of water lost. Well, if this is hydrated, and this is what's left over, so this is going to be anhydrous, the difference between these two is going to be due to the mass of the water of crystallization. So it's going to be 3.57 minus 1.95, and that gives a value of 1.62 grams. So now what you have to do is convert this to moles. 1.62 divided by 18, remember that's H2O, and that works out to be 0.09. Part 2, Calculate the number of moles of anhydrous cobalt 2 chloride remaining. Well, there are 1.95 grams remaining. So 1.95 divided by the MR, or the RFM, of the cobalt chloride, which is CO, it's this part here, CoCl2, that's 130. So that's 0.015. Part 3, calculate the value of X. So here we divide by the smallest one, which in this case is this one. So that divided by itself is 1, and that divided by 0.015 is 6. D, so let's see, we've got a reacting mass calculation. Calculate the mass of the cobalt oxide or cobalt 2 oxide in kilograms. Okay, so we need to remember that. From the reaction of 945 grams of the cobalt 2 oxide. Okay, so I'm just going to draw or write out those two parts. I start off with 945 grams, so I've got to convert this to moles. The RFM of cobalt 2 oxide is 75, so that equals 12.6. It's a 6 to 2 ratio, so it's 3 to 1. So that means it will form 4.2 moles of the cobalt 3 oxide. Now I can just convert this to a mass. So if we go down here, the mass is going to be 4.2 times the MR of this, which is 241, and that gives an answer of 1012.2 grams. Remember, I have to give the answer in kilograms. So we're going to move the decimal place 3 places, and that is going to be 1.01 kilograms. Give your answer to 2 decimal places. You don't want to lose that mark.